Great, thanks. It's a pleasure to be here. So, thanks to Jean Hyun. So let's see. So we have basic means two of the most important objects in algebraic geometry. They are the Chow homology groups and the Chow cohomology groups. So one way, if you want to think of the Chow homology and the Chow cohomology groups as sort of part of the same framework, then you can work with these things called bivariant Chow groups. And as I said, they appear for the first time in the work of Fulton and Macpherson. The paper is in the memoirs of the AMS. So it's a long paper, some 220 pages or something. So, but I mean, if you want to read an exposition, you can just consult Fulton's intersection theory. So these groups unify the concept of Chow homology groups and Chow cohomology groups. So what is the basic idea? So suppose I have a regular embedding of codimension D. Then what we have is refined Giesen homomorphisms. That is, so let me make a diagram. So just for a moment, just so everybody remembers, this group CHKX. This is the Chow cohomology group. By definition, this is the collection of all cycles of codimension K over rational equivalence. Right. So this is the definition. So suppose I have any morphism x to y. So let's start with a regular embedding. So that will be important. So now suppose we form a fiber square. We have a y prime and we have x prime, and we form a fiber square. So now there are these refined Giesen maps which allow us to construct maps from the Chow groups of y prime to the Chow groups of x prime. That is, as we have right up there. So CHK y prime to CHK minus r prime plus d x prime, where r prime is simply the difference in the dimension d of y prime minus d of x prime. So we have these maps. Now for any such fiber square that we can construct over this map x to y. Now this is the basic idea, and the other example would be if I had x to y and this was a regular embedding, I could have used a flat map. I could have used a flat morphism, and then if I had f, that would go to some f prime in this fiber square. So all the squares we'll be constructing are all fiber squares. We'll have nothing to do with squares that are not fiber squares. So now this map f induces this f prime and then f prime star. So we have an ordinary pullback from y prime back to x prime. Right. We have these maps. Now basically the idea of using bivariant Chow groups is to abstract this idea. Now we had only two cases here, flat morphisms and regular embeddings. So bivariant Chow groups are basically arising by working with any morphism in general instead of just these two cases. So for that, basically we will consider morphisms that are made up of these two kinds of morphisms. So we will consider maps that we call LCI, locally complete intersection morphisms, which can be factored as a product of a smooth map and a regular embedding. F equals Pi. So if x and y are smooth, then every morphism is LCI because of that fact that we could go through x to x cross y and y. Now given that, so let f from x to y be a morphism of schemes. Now consider each morphism, f prime from x prime to y prime, fibered over that by a morphism like that, g from y prime to y. Now by definition, a class in that bivariant Chow group. So for every morphism P, now for each morphism, so for any morphism, thank you. Yeah, so for any morphism f from x to y, our plan is to construct a group like this, CHP f from x to y. So this is an abelian group, and the class in this C is actually, as we said in this case, so what we have here, if we had a morphism like this I, which is a regular embedding, it took things from the Chow group of y prime to the Chow group of x prime. So any such C is actually a collection of a bunch of maps. So C is equal to a collection of maps CKG, where K goes over all integers and G varies over all maps from y prime to y. So, and what do these maps do? These maps go from CKG. So given any such morphism, G from Y prime to Y, I can create a fiber square like that. So in that fiber square, it will go from where R prime, remember, is the difference between in dimension between Y prime and X prime. So a collection of such maps. Now these maps, of course, they should satisfy some conditions which, as we say, they are compatible with pullbacks, proper push forwards, and intersection products. So this is what we call a bivariant Chow group. So why are we working with these bivariant Chow groups? What are their basic properties? So as we said before, they should unify the concept of cohomology, Chow cohomology, and Chow homology. So for instance, if I just worked with this morphism, the identity morphism from X to X, this is simply the ordinary Chow cohomology group. If I were working with now X and so this is the structure map. So this is X to spec of K. If I were working with this minus P, then this would be the Chow homology group. So these can be proved, but I have a feeling that this might require X to be smooth. So that might not be complete. I think it's true in general. But now, if we chose some regular embedding I from X to Y, this would be simply the Chow group of cycles with support in X. So as you can see, these Chow cohomology groups, they contain a large class of objects. A lot of things are contained inside them. So if I had a regular embedding, I could think of the regular embedding would give me a class of maps I upper streak, right? So those could be thought of as a class inside CHI X to Y. Even churn classes, everything can be put inside these maps, these groups. So these groups kind of contain a lot of information about pretty much all the Chow groups you have. Now one of the obvious things we can do is we can multiply such bivariant Chow groups. That is, if I have two composable morphisms, F from X to Y and G from Y to Z, then I could multiply and get something in G of X to Z. Why? So I have X to Y, Z, F, G. So I think of a fiber square here. I have a fiber square like this. Now the class in CHQ of G allows me to go from this Chow group to this Chow group, and then the class in the one with F allows me to go from the Chow group of Y prime to this.
But here, do we always suppose that all of the morphisms are LCI and this so that we can construct things?
I mean, to start with, we don't assume it's LCI, but in a moment we will assume it's LCI, so we might just as well start with that assumption. So we will just put down the disclaimer that all the objects we will use are smooth. So if I have this, if I have this situation, so as you can see, we can multiply such classes, right? So if I have a class D here and a class C here, what I will get is a class CD, right? Now, similarly, I can pull back these bivariant Chow groups. Actually, there is a push forward, but we will not even require that. It's actually quite simple. So suppose I have a fiber square like this, and I have a class C in CHP. So this is G, and this is F from X to Y. Now I want to define G star C belonging to CHP F from this is F prime rather, F prime X prime to Y prime. So how do I do that? So what would G star C naturally be? So suppose there was something fibered over this. This is Y double prime to X double prime. So the class of maps is exactly the same as you would get by fibering over this, because this would be a larger fiber square. So G star C. This is just the most naive thing one could do. So this is the pullback of the bivariant Chow group. So similarly, actually, yeah, so I have put down the push forward. So if H from X to Z is proper and F is equal to GH, we can push forward. That is, we sort of pull back by the whole map, first by using the ordinary class, and then we just push forward the Chow group from F from, so how does it work? So let's see. So F is equal to GH. So So there is x and there is y, and f is equal to g h, right? So it's like this. So now, so suppose I have a class here. That means so using the class here, I can go straight from this to this, and then I just push forward whatever I get here. So now basically I started here and I ended up here. So I have a push forward from CHP fxy to gz to y, right? So now we will basically talk about the LCI morphism. So as we said, LCI morphism is f equals pi, smooth, and that is regular embedding. So each okay, maybe that should have been there's some each LCI morphism. Now each LCI morphism has an orientation class. So what is the orientation class? If the LCI morphism was just a regular embedding, then the orientation class would be I shriek. That is, what is the class in the bivariant cohomology induced by that map? If it's a regular embedding, it's the intersection product, I shriek. If it's a smooth morphism, then it's simply the pullback. And if it's and in general it's a composition, so in general the orientation class f is I upper shriek of p star. First you pull back, then you take the intersection product. So that is the general orientation class of the LCI morphism. Now we have this very important formula which we call excess intersection formula. This we will use all the time. So suppose we have a fiber square, and f and f prime are both LCI morphisms, one of codimension d and the other of codimension d prime. Then we want to know, so suppose we have f and we want to pull back the orientation class of f. So that's g star f. But f prime is also an LCI morphism. It also has an orientation class. So how do the two of them compare? So the question is, so notice that if they were actually of the same codimension, that is d and d prime were exactly the same, then actually pulling back the orientation class of f would actually give me the orientation class of f prime. But in general, if d and d prime are not equal, which is what will happen if g is not flat, then I will have to multiply by something here. Here I will have to put c d minus d prime e, where e is the excess normal bundle of this. So this expression, as you can see, is very useful because it just allows me to move orientation classes from top to bottom. So this is one of our key computational ones. Yeah. And so for composable maps, so we have gf, the orientation class of gf will be equal to f dot g. Now as you can see, there could be a question about factorizing a map, right? If you factorize a map in two different ways, do you get exactly the same orientation class? So that is a difficult and interesting check. See Fulton's intersection theory. So now those were the isomorphisms I put up in the beginning. Now that is another important property. There is another key property, that is g from y to z. Suppose that is smooth. Then we have this morphism f from x to y, and then I could multiply it with g, and that would give me a class in CHP minus n gf x to z, right? If g, so I mean this would work for all g, but suppose g was specifically smooth, then this morphism is always there, but then this isomorphism is actually an isomorphism. This is another very important point here. So this, along with the excess intersection formula which we put last time, those are our two most important tools. So this is the key property and that is the other one. So smooth maps have this great property. Now
I have a question. So in case y is then smooth, then we can take homomorphism g from y to the spec of k.
Yeah, and that is exactly what.
Just a Chow group.
Yeah, that is exactly what we will go.
If the target space is smooth, then this relative bivariant one is exactly.
Yeah, exactly. That is exactly what we are going to do.
Okay.
So
it's actually this bivariant one is going to be capturing some extra information if y is not smooth.
Yes.
Oh, I see.
So our first objective is to, construct these cycle class maps. So we have, so from CHP, f from x to y, to, now similarly using cohomology, we can define these objects. CHP f from x to y to h to p f from x to y. So now using cohomology also we could have created a bivariant theory just like this. So using that we should be able to define this. We want to define this map. So how do we go? So as I said before, there will be smooth and projective over an algebraically closed field. And yeah, so this is one small fact. So okay, maybe as Jin Hyun says, maybe x to s it's not required to be smooth. Maybe I'll check with that. So so we will use that fact, and this fact we mentioned before, that any morphism can be factored that way. So those are the three. Yeah. Now, so given a regular embedding I from x to y, we can say that any class C in CHP I x to y will factor uniquely as C equals t dot I. Where, so if you have a regular embedding, you want to take any class in CHP and we want to say that it comes from the Chow group of X. So how do we do that? We just use basically what Jin Hyun said, that is we multiply C by the structure map of Y, and so you have those, since PY is a smooth map because Y is a smooth variety. Now we have a CHP minus D and then PX, so we have to use the fact that both of them are smooth. So and so we have multiplication by PY, and since what the Chow group of X, also we multiply it by the structure map of X. So C dot PY is something in PXX to spec K, which has to be equal to T dot PX for some T inside the Chow group. But on the other hand, PX is simply PY times I. It's simply PYI, so the orientation class spreads again. So we have T dot I dot PY. Now PY is a smooth map, and by that reasoning we can again cancel out the PY. So the thing is, we cancel out the smooth maps and we have C equals T dot I. So it's just a simple computation up and down. So now we have already done it for regular embedding. As we can see, the classes for smooth maps are really easy. So in general, by similar argument, you can show that if it was any F, then you would have C equals T dot F. Then you would have at C equals T dot F, where D is the relative dimension of F. So recall that given a fiber square with regular embedding I from X to Y of codimension D, we have these GSIN maps. Now here is a very important class that we have to talk about. So when we are defining cycle class maps, so we already have resolved every class as T dot F, and we have shown that this T is unique. I mean, the uniqueness can also be proved using to both sides of the isomorphism. You have to just look carefully. So now this is F is equal to Pi. So this is I, P. So we have to define a cycle class for this object. Now clearly this is already in the Chow group. This already has a cycle class. Now P is a smooth morphism. So what do we have to do? So it just acts on cohomology by pullback. So this part and this part are done. So what about this? So how does this I intersection product act on the cohomology? For that we will need to recall that class. That is, suppose we have an embedding I from X to Y. Suppose that we have this embedding I from X to Y. Then we actually have this class in the relative cohomology. Y minus X. And what is this class basically? This class comes in this way. So this you have I from X to Y, and then you have a normal bundle. You have the normal bundle of this embedding, and this is actually the Thom class of that normal embedding, coupled with excision. That is, you take the Thom class of normal embedding. It sits in the Thom class will sit in this, and then by excision, this is the same object as this, and so you have the class sitting here. This is the orientation class. Now what is the most important property of the orientation class? As you can see there, you could take the cycle class of the intersection product on the left side, but on the right side you could just take product with the pullback of the orientation class. So this formula tells us exactly what we have to do if we want to know what a regular embedding does on cohomology, right? So instead of taking the shriek of that, we could just multiply by this. So now it's quite clear. And the other thing which we will need, we will actually need that for uniqueness verifications. So that if I prime is also on top of that, that is also a regular embedding of codimension D prime, then actually, so then you have two intersection classes. So I prime is, suppose it was another regular embedding, then this has an intersection class U prime and this has an intersection class U. And that formula is telling us how the two intersection classes would be related. So not surprisingly, they are related by multiplying in between by the excess normal bundle, right? So this is exactly saying, so look at the, so that is just expressing the difference. So it just tallies up. So yeah. Now here we have to be a little more careful. So let us go through this lemma. Maybe we'll talk about this lemma when we come to the uniqueness verification. We'll come back to this one. So let's just go ahead and define the cycle class map. So now it's pretty clear what we have to do. So suppose we have some x prime to y prime favored over x to y. So as you can see, py is the second map. So start with the class in the cohomology of y prime. Just apply py prime upper star and pull it back to x cross y by x cross y prime. Then you multiply by the orientation class of if, which is that embedding, and that takes you to the orientation, so then that brings you to the cohomology class of x prime, and then multiply by the cycle class of t, and that gives you something in x prime. So is that clear? So suppose you have c in chp fxy, so c is equal to some t dot f, so where t is in the Chow group of x. So what we do is, so we start by taking the following map. So first we pull back py prime star to y prime, so that brings it here. To move from here to here, we multiply by the orientation class, as we said, and then we had the t, which just has an ordinary cycle class in the cohomology, and we multiply that. So that is how we get the cycle. So that is how we move from the cohomology of y prime to the cohomology of x prime. So this is the definition of the cycle class map. Now you might ask that this has been defined with respect to a very specific embedding. We put x inside x cross y and then brought it down to y. What if I had gone another way? So suppose this map from x to y, I could have factored it through some p. I could have done this way. If I had that way, then also what would I have done? I would have pulled back here, multiplied by the intersection class, and then multiplied by the cycle class of the Chow group. So would I have got the same thing? So for that we have to talk about that lemma. So now there is a question about, we have a little bother about uniqueness. So there what we do is suppose we have to prove this lemma, that suppose we have a regular embedding which can be factorized as a smooth map and another regular embedding. Then what you can actually do is we have to prove a relation between so ui is the orientation class with respect to the embedding I, and uj is the orientation class with respect to the embedding j. Then we have to prove a relation between the two orientation classes. And the main thing to notice here would be that if you have this factorization, then the difference in the I minus I prime, the relative dimension difference, is the same. So which kind of tells you that the two normal bundles have the same Chern class. So this is slightly long proof. So this is what I was saying. So suppose that alternatively f could be factored in another way through some other p. So then we could have done pretty much the same thing. You pull back to q, then you multiply by the intersection class, and then you multiply by the class of the original Chow group. So how do we know they are exactly the same? What we do is, suppose we had two such factorization, one through p1 and another through p. So we just construct this fiber. We just consider this fiber product, and then as you can see over here, so we will compare both factorizations to this. And where does the previous lemma come in? You see that in this one, this is a smooth map composed with a regular embedding. This is still a regular embedding. That is what we had last time. So let's just go back to that slide. You see, we have a regular embedding j from x to y, which factorizes as a smooth map and a regular embedding. And this is exactly what we have in that one. From x to p1 is a regular embedding. This is smooth, and this is also a regular embedding. So this is how we have to construct so there is a sequence of lemmas here, and we have to finally show that they are actually unique. So in general, so what are the properties of this cycle class map? So suppose in general that f prime is fibered over f from x to y and g from y prime to y. Now this commutes with pullbacks. There's also a little So these take a while, each of these proofs. So, and the other one is that this actually behaves well with respect to ordinary classes, that is ordinary cycle classes, that if you started from CHKY prime and went down to H2KY prime by the usual cycle class map, and then you used the bivariant Chow group, the bivariant Chow map to go there, and CLC to go in that direction, would actually have commutative diagram. So this is well behaved with respect to ordinary cycle classes, and also it is very important that it behaves well with respect to products. That is, class of C dot D is the same as class of C times class of D. So, yeah. So now we have come down to a certain use. So now that we have defined the cycle class map, we are now, so we will be doing one of the main uses today, and we'll be doing the other use in the next section, when we will try to work with bivariant version of blocks higher Chow groups. But for today, the first use and basically the only use we'll make today of that is working with with Bailinson's conjectural filtration on Chow groups. So we have a filtration already due to Saito, which is already a little mysterious. But there is a decreasing filtration, which is.
Before we go on, can I ask you one question? So for a given morphism of varieties, you have defined the bivariant Chow groups, and generally, this morphism can be considered as a graph over x cross y as a correspondence. So if I have then an arbitrary correspondence between x and y.
Yeah, I have been thinking about that. I have been thinking about that. So I mean, I expect that you just the main part of that morphism is so if you had a correspondence like this, right? Something like this. So you could start with the bivariant Chow group of this. So the classes could be taken by, in general you could define something which simply starts with something fibered over y and starts here and goes here. Now the question is, how would it be related to what we have already? So as far as I believe, you could, so if you had something like this, CHP, so I'm not sure of this part, but if you had something like this, so this thing, I have, as far as I understand it, there would be an embedding of, if this map is some F. Because you could take this and you could pull back and get these. I believe it's possible to show that this is an embedding. I have been thinking about that. I have not worked that out.
If there exists, it should be a bigger group.
Yeah, I think this is a bigger group.
I see.
You could, but the definition is pretty clear that you could just have anything that is a family of maps from here to here, but then you have to be very careful in defining the conditions of compatibility with intersection products. There will be a lot of confusion, but I believe one can define that. And in general, there should be an embedding. I'm not particularly sure whether this will be an isomorphism or not. So we have a decreasing filtration due to Saito on the Chow groups of a projective variety X. So this is a candidate for block Bailinson's filtration, which is supposed, we will mention some, there are of course many other conjectures about this filtration, but let us mention three important properties which Bailinson wanted. One is that it should be sort of respected by every algebraic correspondence gamma, and the induced action of gamma on each graded piece depends on a certain, so due to some ignorance of LaTeX, the Kunet has become a little weird. So maybe I should have learned some command, but there's an umlaut or something like that, right? And I probably put some wrong command over there. So anyway, so suppose some Kunet component, and the filtration should terminate. The third major requirement is that. Now, interestingly, Saito has proved the first two, but he's unable to prove the third one, which kind of looks like the most innocent of all. And what one can show is that if the filtration which Bailinson wanted, that is supposed to follow from a theory of mixed motives. If that theory works, then up to rational equivalence, this is supposed to be the same as his equation. But not rational equivalence, tensoring with Q. So up to a tensor with Q, this should be the same as the filtration Bailinson wanted, in case the theory of mixed motives he expected to be true is true. So that is what Saito proved. So now our purpose is to extend this filtration to the bivariant Chow groups. Now there is one obvious way to do this. So you could, since you have a map you could just multiply the Chow group with the orientation class. So that is one obvious way. You already have the filtration on the Chow group. You just multiply by the orientation class and get classes in CHP FXY. So that is one obvious way. to extend the filtration. But I mean, it doesn't teach us anything. So what we will do is we will look more carefully at the method of Saito, and then we will show that what we actually have from within his results is actually what is supposed to follow. So what we need here is a more general push forward. That is a map like that. That is CHK from V cross X to V cross Y. We want a push forward like that, which goes to CHK X to Y. So now I keep forgetting the sequence of maps. So here is the sequence of maps that we need to do. So we want to start with a class in CHK V cross X to V cross Y, and we want to end up with a class in X to Y. So we already have a class C belonging to CHK V cross X to V cross Y, and want class in CHK minus dV as it appears to me, X to Y. This is what we want. So how do we do this? So in order to get that class, so we'll explicitly create that class. So suppose we have X to Y and we have X prime to Y prime. So how do I know I would have a class here? I want a way to go from the Chow group of Y prime to the Chow group of X prime. So how do I start? So given something in the Chow group of Y prime, I first pull it back to the Chow group of V cross Y prime. Now, if this is a fiber square, certainly this is a fiber square. So now that I have something in the Chow group of V cross Y prime, I can use this class in here to go to the Chow group of V cross X prime. So that's the second map. And once I am in the Chow group of V cross X prime, I just push it back by the projection, push forward by the projection rather, and I get something in X prime. So that gives me, so basically I have started with something in Y prime and gone to something in X prime. So I have a class in CHK minus dV X to Y. So now that I have this, and I could have equally done this on cohomologies. So we have got this map. Now one has to check, this is again a rather complicated check, that if the map we were using F was simply the identity map, then this would be the ordinary push forward from V cross X to, from Chow group of V cross X to Chow group of X. We have to actually check that. It was also a little new proof. So now, maybe before we do this slide, we should talk about the filtration of Saito first. So that we get a sense of why we are doing it. So Saito's original definition goes like this. So since it's a decreasing filtration, we naturally start with F0 equals CHK of X equals CHK of X. Now suppose that for some nu greater than or equal to 0, we have, so this will be inductive. So we have already defined all the F nus up to that point. And now we want to talk about F nu plus 1. So that is, as you can see, is equal to a sum over all the maps from the push forwards due to correspondences. That is why we are constructing the more general push forward. We have to still do a little more work on that. So the point here is that you see a push forward by a correspondence rather than a map. So that is what we are actually doing for bivariant Chow groups. That is what we are going to construct. So you work with all V which are varying over smooth projective and dimension dV over C, and there are some basic conditions over the Q and the K so that everything is positive and all. And then there is a certain condition that we impose on the class of correspondences. So we will just copy that condition. What we will change is that we will push forward on the bivariant Chow groups by correspondences. That is why we will replace those maps.
What is this N with K minus 3?
Oh, that is the Univ filtration.
Composable filtration. Okay.
So, this, as you can see, is the Kunath component. We said that the should lie in a certain Kunath component. So in our definition, what we will basically do is, so you can see a push forward not by a map but by a correspondence. So what we will do is, instead of gamma star, we will have to construct a map on bivariant Chow groups, which we will be pushed forward by a correspondence, and that we will call the map TK gamma. So we are still in the process of constructing the map TK gamma. So let's see. So, and the gamma in general, last time it was on this slide you can see gamma lies in CHQ of V cross X. So in our case, it will now be something in CHQ of V cross X to V cross Y. It will be a more general object. And so now, depending on that, we will define this map from CHK plus dV minus Q to CHK of XY. So what is the way? So what we have is we just pull back from V, we pull back to V cross X. That's the first step. Once we are at V cross X, now what is CHK plus dV V cross X? We know that this is already CHK plus dV, one identity going from V cross X to V cross X. So I can simply compose it with gamma which lies in CHQ, I believe, of V cross X to V cross Y. Right? So this is one going from V cross X to V cross X and V cross X to V cross Y. So I just multiply. So gamma allows me to multiply. That's what we do. We pull back, we multiply by the correspondence, and then we push forward. And then, so now I have an object which lies in V cross X to V cross Y. But last time what did we do? We just defined a push forward like that, which goes from V cross X to V cross Y to F from X to Y, in case you have already forgotten. That is the map on top. We have defined a map like that which goes from there. So at the final stage, instead of using the ordinary push forward, we'll have to use this push forward, which takes us down to CHK FXY. And the stuff below that is just, we have to just carry on the condition in the QNet component, which we will be just pasting. So that is sort of the backroom calculation. So as I said, in our definition, we will replace the gamma star by these maps, TK gamma. Now, so what is our definition? So this is a slide. So once again, we will say that G0 is the whole group. And again, we will inductively assume that we have already defined up to G nu for all these maps. Now, the G nu plus 1, we are arranging over exactly the same objects, but this time the gamma star has been replaced by the map TK gamma, which we defined, and we have that. And this condition, the QNet condition, as you can see, they have all been pasted. Now, so first of all, in fact, this is not even clear, first of all, that this is a filtration. Even that is not clear. So what we have to do is, so we have just constructed these subgroups of CHK. Now, first of all, it's not even clear it's a filtration. So now we have a main theorem in which we show that this is actually agreeing with the naive extension of the filtration from CHK to FXY. In the beginning, we said that there is an obvious way to extend the filtration, that is just multiply by the orientation class, right? Now we can say that this agrees with the naive extension of this filtration. We show that each of these G nus is the same as what you would have got, say, some G prime nu or something. And that actually proves that this is a filtration. Because that one is obviously a filtration, we just multiplied. Now, since these objects agree with those objects, it's got to be a filtration. And the two of them agree. So this is one use we make of the cycle class map. So in the next talk, we will be talking about a bivariant version of block Chow group. So I think I finished a little early, as I always do.
So maybe you should give us some details now.
I mean, unfortunately, I've run out of slides.
I think that maybe you want to slow down a bit the next time. Okay, so I still have some questions.
Yeah.
Bloch-Bayes conjecture requires some filtrations of Chow groups to satisfy certain conditions.
Yes.
What kind of, so if you want to do the Bloch-Bayes filtration on the bivariant Chow group, then there should be some kind of motivating reason, such as some kind of bivariant version of the Bloch-Bayes conjecture.
I mean, I've been thinking about that, but it's rather hard. It's still on the sort of block, on the cooking sort of stage.
Okay, so
that part.
There is not yet some.
No. I have to increase this. No. I have to increase this section.
Is actually related to the question actually I had about. So in case I have f which is morphism from x to y, where y is supposed smooth, then we had actually a statement of theorem that then we can actually take the structure morphism from y to spec k, and that actually gives an isomorphism of the bivariant Chow group with the Chow group of x.
Yes.
Then so the new information comes out when y is actually not necessarily smooth.
I mean, to get the isomorphism, I think you will also need the fact that x is smooth.
X is smooth?
You need that as well. So because I think the isomorphisms are not there unless x is also smooth.
Both x and y
yes, we will need both.
Okay, so then, of course, if the bivariant Chow group is actually coming from the Chow group, then there's nothing new to study, right? Unless you have some new functional reality.
Well, I mean, the thing is that the bivariant Chow group, it kind of contains all the all the information about the, I mean, the main point in this one was to construct the cycle class of the orientation classes. That was the biggest motivation here. Not really the Chow group, because as you saw, the Chow group just appeared as a cycle class on the left side. It was just coming by. The whole action is on the orientation classes.
So actually, so in case the X and Y are smooth, it makes the construction of that orientation class easier to see.
Yes.
In a more
Yes.
structural way.
Yes. I mean, I'm wondering what to do if they are not smooth. I'm still not sure what to do with the orientation.
Construction is not easy. So
Yeah.
this one
How
allows
the
us to see
yes,
how
yes.
we can actually make
Yes.
this kind of class
Yes.
relative. I really don't. Okay. But still, the question is then. So this group itself is not going to be new at all in case X and Y are smooth. So if we want to have a new group which is bigger than the usual child group, then we must require
at least one of them.
non-smooth,
Yes.
right? At least we
Yes.
must have something
Yeah.
developed.
Actually, what I should mention here is that there is a lot of effort on this, particularly by somebody by the name of Brasselet, I believe. I mean, he has been working with the cohomology group, but what he has not been using is so I think the point is about the definition of the bivariant cohomology group, which was not stressed very much. There are some people who just want to define it as the relative cohomology, but the point of this is to see the cycle class is easy if you define the bivariant cohomology groups in a certain way, that you just bivariantize the cohomology construction. But there are some people who define, so it's actually they do it specifically for not just for smooth varieties, only for smooth manifolds. So it's a rather involved problem. It has not progressed much beyond the smooth case.
Okay, so also I had a question about this cohomology. So this construction work on for arbitrary value cohomologies H? So here you said that variety is actually smooth generally, variety over arbitrary algebraic closed field, maybe it's characteristic 0. But the H was not actually specified as what kind of cohomology.
Well, I mean, as long as it has that property of the Weyl cohomology, that it has a map from the Chow group,
so
I don't think there is a problem. Yeah, I think so.
Any kind of
As long as there is a cycle class map from the ordinary Chow group, I don't think there is a big problem.
So such vague cohomology.
Although we have to be careful if we have Thom classes and everything in arbitrary.
I'm not sure if that is
I have never come across that.
So in case if it is the base field is complex field, then we actually certainly use the Ram cohomology.
Yeah.
And that's going to be fine for this. What about type cohomology? In that case, we do have some kind of Thom class.
No, I haven't seen the construction myself.
I never heard of that kind of thing.
I mean, it has to be seen carefully. So I mean, by cohomology here, I basically meant ordinary singular cohomology or Dirham cohomology. But yes, but as long as the Thom classes are fine, it should be fine. But for that, I have to see.
I mean, for the type cohomology, the Thom classes are fine, but the relative cohomology are not quite defined. It just uses some kind of purity result.
Yeah, there is some kind of complication with the more arbitrary cohomology groups, but that has to be seen separately. So.
Okay. So in case X and Y are not smooth, do you possibly have some examples?
I mean, actually, I've looked up the literature on bivariant Chow groups, and the work really has not progressed very much beyond the smooth case, because there is some. I think Yokura has some result if by resolving singularities, but they are very, very specific, and has progressed very little. So.
I see.
This almost beyond the smooth case, it's pretty much where Fulton and McPherson left it, wrote it and left it. So it's where it is. It was I don't know when that paper was written, 1986, I believe. So more than 20 years ago.
So I guess maybe I asked somebody who has some other questions. Okay, so we are still more time, but more questions. I guess maybe you can thank the speaker. We are going to be having a